Welcome to True Projects. In this video, we are going to explain about detection and isolation of sensor attacks for autonomous vehicles, framework algorithms, and validation. Introduction. The project examines how autonomous vehicles can be vulnerable to cyber attacks due to their reliance on multiple sensors for localization and perception of the environment. The project focuses on detecting and identifying cyber attacks using two widely used sensors, GPS and LiDAR. The project presents a thorough examination of existing techniques to addressing the cybersecurity challenge for autonomous cars, which can be divided into two categories, information-oriented and control-oriented. The project presents a model-based approach for detecting and identifying cyber attacks on autonomous vehicle sensors, which has been validated using data from a real self-driving vehicle. Objective. The project's objective is to address the cybersecurity difficulties that autonomous cars confront, notably the detection and identification of cyber attacks on GPS and LiDAR sensors. The project presents a model-based approach for detecting and identifying such attacks, which has been tested using data from an actual self-driving vehicle. The project also presents a thorough evaluation of existing techniques to addressing the cybersecurity challenge for autonomous cars, which can be divided into two categories, information-oriented and control-oriented. Requirements. The requirements of the project are hardware requirements and software requirements. In hardware requirements, we have operating system, Windows only, processor i5 and above, RAM 4GB and above, hard disk 20GB and above. Software requirements. In software requirements, we have Python IDEL with 3.7 version. Methodology. To implement this project, we have designed the following modules. The first module is upload GPS dataset. Second module is upload LiDAR dataset. These modules involve loading the GPS and LiDAR data collected from sensors on an autonomous vehicle. GPS provides location information while LiDAR provides detailed 3D point cloud data of the surroundings. Third module is run GPS extended Kalman filter. The extended Kalman filter EKF is a mathematical technique used to estimate the state of a dynamic system from noisy sensor measurements. In the case of GPS, the EKF can help improve the accuracy of vehicle's position and velocity estimates by fusing the GPS measurements with the vehicle's motion model. Fourth module is run LiDAR extended Kalman filter. Similar to the GPS EKF, the LiDAR EKF combines LiDAR measurements with the vehicle's motion model to enhance the accuracy of the point cloud data. It helps correct for noise and uncertainty in the LiDAR measurements. Fifth module is run rule-based QSIM detector. QSIM stands for cumulative sum. A rule-based QSIM detector involves setting up rules to detect changes or anomalies in sensor data over time. This module likely focuses on detecting deviations in sensor measurements that could indicate sensor attacks or anomalies. Sixth module is attack detection graph. The attack detection graph likely visualizes the results of the attack detection modules. It shows when anomalies were detected, the severity of these anomalies, and possibly whether multiple sensors detected similar anomalies. Execution. For the execution of the project, we need to open the code folder. This is the code folder. This is the dataset folder. To implement this project, we have used the GPS and LiDAR dataset. This is the main code file. This is run.batch file. Instead of executing our project in the command line interface, we have created Windows batch file to execute the project. Double click on run.batch file. This is the graphical user interface. We have created this GUI using Tkinter library in Python. Using this GUI, we will interact with the project. Click on Upload GPS dataset to upload the GPS dataset. Select GPS and open. We can see that the GPS dataset is loaded. Now click on Upload LiDAR dataset to upload the LiDAR dataset. Select LiDAR and open. We can see that the LiDAR dataset is loaded. Now click on Run GPS Extended Kalman Filter to run EKF on GPS data. So here we can see that we got the original GPS latitude and longitude and EKF predicted latitude and longitude. In above screen for each original GPS location, EKF has predicted next location, and if we scroll down we can view all the values. Now click on Run LiDAR Extended Kalman Filter to apply EKF on LiDAR dataset. In above screen, for each LiDAR original latitude and longitude, EKF has predicted location, and we can see there is narrow difference between original and predicted values. Now click on Run Rule-Based QSIM Detector to find variations between original and predicted values, and then run rules to raise attack alarm. In above screen, for each latitude and longitude, QSIM has applied rules to detect attack, and in above screen, in blue color text, we can see GPS and LiDAR attack detected, and in other records, no alarm detected. If we scroll down, we can view all the detections. Now click on Attack Detection Graph to get the graph. In above screen, we developed code for 2 detectors, and we can see alarm and no alarm for both detectors. And in below is the other records output. In above screen last lines, we can see only LiDAR attack detected, and below is the detection graph for both the detectors. So this is the GPS and LiDAR attack detection graph. X-axis represents time and Y-axis represents attack detection count. And red line represents GPS attack and green line represents LiDAR attack. And in above graph, we can see GPS detector 1 detected total 4 attacks from 0 to 120 record. And LiDAR detector 2 detected 7 attacks. Now close the graph. Close the GUI, and the final conclusion of the project is the project concluded that the suggested model-based approach is effective in identifying and isolating cyber attacks on autonomous vehicle sensors. The system includes a bank of attack detectors and a rule-based attack isolation strategy that not only detects but also identifies sensor attacks, considerably improving autonomous vehicle cybersecurity. Experiments on real vehicle data revealed the efficacy of the suggested framework, which thoroughly examined 4 categories of common attacks, including FDI and replay attacks, and generated 7 attack scenarios based on them. Experiments have shown that by providing an extra detector that checks the inconsistency between several sensor values, GPS covert attacks can be identified, allowing them to elude detection.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.